Okay. All right. And then same thing, we're going to fill in the right array. And then here it's going to be mid plus 1 plus j. All right, because we know the right is past our midpoint, so it's going to be mid plus 1. And then to offset it to the correct index for our subarray, it's plus j. That makes sense to you guys? Why we do one plus 1 for mid and not for the low? Yeah, Matt. So when we're dealing with the left array, let me bring it over here. When we're dealing with the left array, it's everything from the starting index of the original array to the midpoint, right? So let's say we get down into here, right? Just because we're passing in our low for each recursive call. So our low can be a different value each time we're doing our allocation for the subarrays, right? So we want to make sure that when we're accessing the original array, it's at our current low plus our current iteration of I in the for loop, right? And we don't have to worry about the plus 1 because it's everything before the midpoint. When we're dealing with the right half of the array, we're past the midpoint. So that's why you have mid plus 1 because it's everything past the midpoint. And then to make sure you're in the correct position inside of that subarray, it's plus j. Okay. So we've allocated our memory, we've filled in our subarrays. This is where we're going to start doing our merging process, but we need some variables to help us do that. So I'll say int I j is equal to 0. You can do this as two separate lines if you want. I'm just doing it as one. And then we'll say int k is equal to our low. This is where we're going to start our merge process. And we're going to use a while loop. So we'll say while I is less than the left size, right? And j is less than the right size. This is where we start doing our sorting, right? So if array, I'm sorry, left array I is less than or equal to right array at index j, we're going to say in our original array k at index k, so k is equal to our low, is going to equal left array at index I. And then we'll also iterate I. And then if it's the opposite case, if left array I is greater than right array at j, we'll say the array at k is equal to right array j because it's the smaller value. And then we'll increment j. And then we'll increment k outside of the if else loop. This is still void merge. Sorry. I don't have any main functions so far. And then let's say that there's remaining elements of either the left or the right. We're going to double check for both of them. We'll say while I is still less than the left size. We'll just fill in the remaining spots of the array. And then we'll increment I, increment K. So we handled the left. Let's handle the right. I'm gonna run out of room. That's fine. Let me resize all this to fit everything. Okay. And then after we're done with our subarrays, we did malloc statements, so we need to free them, right? And then we're done with our merge function. So just to reiterate, when we're calling our merge function after our recursive calls, we're going to get the left size, we're going to get the right size, we're going to allocate the memory for the left array and the right array using the left and the right size that we just captured. And then after that, we're going to fill in the subarrays. After we fill in the subarrays, we're going to do our comparison for the sorting. We're going to see if first, we're going to see if the left array at index I is less than or equal to right array at index J. If it is, then in the original array, we're going to overwrite at index K, which is set to our low currently. We're going to overwrite it with the left array at index I. We're going to increment I. If it's the reverse case, then we'll say array at index K is equal to our right array at index J. We'll increment J. And then outside of that if else check, we'll increment our K. And after that while loop, we're going to handle the cases where, let's say, for instance, like our left array is larger, our left subarray is larger than our right subarray, right? So if we hit that case, then we need to make sure that we're still pushing those remaining elements into the original array. And that could be for either case. It could be for the left array or it could be for the right array. So we'll do two more while loops and we'll just make sure that while I is less than the left size or while J is less than the right size, we're overriding in the original array at the current index of I and J for left and right. And we'll increment I and J and also K, and then we're freeing our subarrays. Does that make sense to you guys? Okay. What exactly are we comparing at the in those two arrays? So we're comparing the values. So the current elements, I should say. So I guess it wasn't big enough. Or we're comparing the elements at their respective indexes. So for instance, this would be like our left and our right. We're comparing is 10 less than or equal to 2. 10 is obviously greater than 2. So then our check over here, our if statement would fail and we would hit our else statement. And we'll say that in the original array at index k, which is our low, we'll set it equal to right array of j, right? So then we end up with 2, 10. Does that make sense to you, Bree? Okay. And then obviously for each recursive call, you're doing that merge check. And then that's how we end up with our base case. You see this and it starts combining, right? And then these two combine, right? Combined, this just goes there. And then these two combine. That's a merge check. This is another merge check. Does that make sense to you, Bree? Okay. All right. Any questions on merge sort, guys? I'm gonna take that as a no. Okay. So then I'll jump into quick sort. And so for quick sort, guys, it's very similar. I shouldn't say very. It's similar in the fact that it's an n log n function, and it also uses this divide and conquer methodology. But inside of the conquer step is where we're also going to be doing our sorting, so we don't need to have a separate combine function, right? Inside of quicksort, we have what is called a partition, and then there's a couple of approaches to pick a partition. Um, the first approach would be like choosing the first element and making that our pivot. Um, uh, our second case would be choosing the last element and making that the pivot. There's the median of three approach for the pivot, which was the extra credit on the homework. And then the last approach would be choosing a random index or a random number and making that our pivot. Okay. Um, and then so our partitions is basically going to be we're going to partition the array so that the left side is going to be all numbers that are less than or equal to our pivot. And then the right side of the array is going to be all the numbers that are greater than our pivot, right? So let's make this as an example. And I'll zoom in for you guys. Let's say we have 3, 8, 9, 11, 1, 6, 4, and 7. And we'll make 7 our pivot, right? And so we're essentially going to check this entire array. Oh my gosh. So we're going to say is the array at some index less than or equal to our pivot, right? That's essentially what we're going to be checking. And so we'll increment through the array in our normal way. we'll just have to keep track of certain elements, and I'll show you what I mean by that. All right, so this is our pivot. And we'll start with 3. We know that 3 is less than 7, so we don't have to keep track of that. We know that 8 is greater than 7, so this is where we want to start keeping track of this. And we'll call this our call this J. 9 is also greater, right? I'll show you step by step. Let me not jump ahead. We'll call this J.
We do it again.
So we see that 9 is also greater than 7. So then we'll move our J over. Um, we'll move our J over. And then we'll continue down this path, right? Until we find some value that's less than our pivot. Right. And I'll just jump ahead. And I'll get straight there for you guys to show you what happens. So this is our J. So what's gonna happen is that we're going to swap J. Sorry to tell you guys, this is I. We're gonna swap J with I plus 1, because I plus 1 would be the first element that's greater than a pivot, right? So when we do this swap, we end up with 3, 1, 9, 11, 8, 6, 4, and 7.
I'm so confused.
You guys see how that works? And we'll continue doing this check, right? So our new like high elements would move from here. And then it'll move to here. So we'll keep on checking, right? So 6 is less than our pivot. So then our array moves. So 3, 1, 6, 11, 8, 9, 4, 7. All right. And we'll keep on checking. 4 is less than 7. So then we'll have 3, 1, 6, 4, 8, 9, 11, and 7. And then this is essentially sorted, but it would have to continue finishing through. That's why it's n log n. And then after we do that, we need to do our final exchange between excuse me, I plus 1 and our pivot, right? So then after we do our final exchange, it'll be 3, 1, 6, 4, 7, 9, 11, and 7. You'll choose a new pivot and then continue going down the same path of sorting from the left, items less than the pivot, and on the right, items greater than the pivot, and sorting the array. Does that make sense to you guys? There shouldn't, I don't believe there should be two sevens because you swap your pivot because you move your pivot to the end of the array. And then when you're done with your sorting of that rotation, you swap your pivot with whatever is at I plus one. Oh, sorry. That will be eight. My apologies.
You're okay. Forget.
And see, I guarantee you.
That's good for you guys. That does that make sense for you guys? So then like your new pivot, like you choose another pivot and like for instance, you could do like four and then you would sort everything. You would move four to the end. Um, and then you'd sort the array into the left and the right side again, and then move forward back into its original position or where it should be at I plus one. And then if that's finally sorted, you're good to go. That makes sense to you guys? And then we can go over the code as well. So there's two functions. We have the recursive call, and then we have the what we call the partition function. So to go over how the pivot's usually chosen, show you. Remember, we have our
You know what I love, dude?
approaches for the pivot. One is choosing the first element.
Yeah.
Second is choosing the last element. Third is the median of three. And then the fourth is a random number. So that's how you choose. I chose just the last number as the example, just to show you guys. I'll show you guys that approach and then the random number approach.
Hey,
Peace.
peace.
That makes sense to you, Bree? Maybe I'll scroll down a little bit. Okay. So let's go over actually coding it now. So like I said, we'll have our recursive function. We'll need our array. We'll need a low. We need a high. And then our base case is the same as merge sort if low is less than high. We'll do our work inside the recursive function, right? So we need to find our pivot index. And we're going to get that from our partition function, right? And I'll go over the partition function right after this. We're going to pass in our array. We're going to pass in our low. We're going to pass in our high. And then we're going to recursively sort the left and the right of the arrays, right? So we'll call the function again. We're going to pass in our array. We're going to say low is still going to be the same low, but our high is going to be pivot index -1. And then we have our second recursive call. We're going to pass in our array again. We're going to say pivot index +1. And then we have our high. That's our recursive quicksort function. And then this is where we get into the actual sorting in quicksort. So we're almost made it void. If you remember from up here, we're returning some integer as our pivot index. So our partition array has to be of type int. And then as you see here, we still need an array. We need a low index. We need a high index. So to get our pivot value, again, I told you I would show you two approaches. This approach, I'm going to show you just using the last element as the pivot. And then we need int I is equal to low -1. And then we need to do our for loop, right? So we're going to have for int j is equal to low. J is less than or high. And we'll increment j. And then we're going to check. So we're going to say if array at index j is less than or equal to our pivot, we're going to increment I first, right? So this handles the case. This is where I was getting confused of a merge sort earlier. So let's say I is -1, and we're starting at the first index 0. I would be -1. We're going to increment I first. So make it I is equal to 0. We won't get like an array out of bounds error. And we need to perform some swap. So we're going to need a temp, and it's going to store whatever value is at array at index I. And that in array index I, we're going to set it equal to array at index j. And then array at index j is going to equal our temp value. We're performing a swap, right? So j is less than the pivot value. So looking back at this here, so I starts at -1, j starts at 0, and we're going to check is j less than or equal to the pivot value. 3 is less than or equal to the pivot value. We're going to increment I, right? So I would equal to 0. We're going to create a temp, and we're going to swap. So we're going to swap array I with array j. So for the first check, right? So this is what she was talking about in class, where she says like the first iteration. So for instance, 3, you'd basically be swapping it with itself. And then we would move forward, right? So I would stay at index 0, and then our j would move forward, right? So then j is at 8. We're going to check is 8 less than or equal to our pivot, which is 7. It's not. We're going to increment j. So is 9 less than or equal to our pivot? It's not. We're going to increment j again. Is 11 less than or equal to our pivot? It's not. We're going to increment j again. And so now we hit 1. Is 1 less than or equal to our pivot? It is. And this is where we perform our swap, right? So then we're going to swap again, just looking back. We're going to increment I. So I moves from 3 to 8, right? And then we're going to swap that 8 with that 1 and continue doing our sorting. Okay, so that's the actual sorting portion of this, right? Or at least the swapping. Now we need to place the pivot, like I was saying, into its correct position. So we'll need another temp again. And we're going to set it equal to I plus 1. And then we're going to say at array I plus 1 is equal to array high. Why? Because our pivot is our last element. So we're swapping at I plus 1 with our high. And that's the final swap that we were discussing. Where'd it go? Here, right? And then we'll say array I, my gosh, it's equal to our temp. And then we'll return, because remember we're expecting some integer value, I plus 1. And that is the end of our partition function. And this is the case using the last element as our pivot. You guys good there? You need me to zoom out some? I'll zoom out a little bit. And then I can go over the random approach. I'll just write it. Yeah. Oh my Atlanta. Okay. So int partition, same thing. Meter array, meter low, meter high. For this one, it's going to be, we're going to use our random function in C. So we're going to say int random index is equal to low plus our random function call mod high minus low plus 1. Okay. In her notes, she created a swap function. And then she just called swap on the array itself. I'm going to show you the manual way to do it if they don't give us the swap function. So we need a temp. And we're going to set it equal to array low. And then we're going to say array low is equal to our array at the random index. And then array at random index equal to 10. That's the swap that she's doing. When you see that swap and then it's saying array low with array at random index. This is that manual work that they just skipped. And then moving forward, we're going to have an integer and we're going to call that our low position. And we're going to set it equal to low, right? This is our pivot. And we're going to say low plus plus. And then we're going to have two while loops. Our first while loop, we're going to say while low is less than or equal to high and array low is less than or equal to array low position. What are we going to do? We're going to increment our low. And then in our other while loop, it's going to be the same first check. So while low is less than or equal to high and array high is greater than array at our low position, we're going to decrement our high. Then we're going to have our check. We're going to say if low is less than high, we're going to perform another swap. All right, so we're going to say integer temp is equal to array low, and then array low is equal to array high, and then array high is equal to 10. After that, we just need to return our high. Not a bracket. Failure. Okay. This is our random number approach. You guys can see that pretty good. I think so. I think there's probably going to be like maybe one or two questions. Like she might say like, "Oh, write the insertion sort algorithm," or she might say like, "What's wrong with this merge sort function?" Um, then apply the fix to make it work, something like that. I don't think it's going to be anything that's just outright crazy. The one thing I think everybody is like glancing over is trees. We're probably gonna have like one tree problem, and it's probably gonna be like a traversal problem, if I had to guess. So do you guys know the different traversal techniques for trees? The in order, pre-order, and post-order traversal. Does that ring a bell? Okay. You want to look at recurrence relations first? Yeah, we can. We can. Trees seem easier. Okay. Are you guys fine with summations then? It's just the recurrence relations? Okay, just the basics. Okay. All right. I'm just looking over her notes again. I'm sorry, guys. All right. So we know with recurrence relations, we're going to have our T of 0, which is essentially our base case, and then our T of n, which is our recursive calls, right? And then T of n is equal to C1 plus T of n minus 1, so long as n is greater than 0, right? And then T of 0 would equal C2. Let me see if I can find a practice problem for this. Recurrence relations problems exercise. There we go. That's the exercise. Is there a certain problem you guys were struggling with or wanted to look at? The one in the labs are hard. Okay. So I have her recurrence exercise pulled up. So like for instance, this one is T of n is equal to T of n minus 1 plus 2, and then T of 1 is equal to 1. Um, so she basically gives us our base case, which is the T of 1 is equal to 1. So essentially, like whenever a function gets to some value of 1, we're going to return 1. That's what the base case is. And then the recursive call is going to be T of n minus 1 plus 2, right? So we're going to call the function with n minus 1, and then we're going to add 2 to that value. And that's what we're going to be returning, right? So we need to substitute n for n minus 1. Okay, so we'll have like T of n is equal to T of n minus 1 plus 2. And then we need to, again, do our substitution, right? So we'll have T of n minus 2 plus 2, right? Plus 2 is equal. Do I have room over here? I don't. I'm writing too big. It's equal to our T of n minus 2 plus 2.
Now we are losing.
Oh. Are you trying to ask something, Bree, or your mic just popped on? No, you're good. You're good. Um, and so essentially you it's like pattern recognition. You have to see like the pattern it's forming as you do your recursive calls, right? So you're probably wondering like where did you get this times two from? Um, you can see it like right here. So you have your function call here, and then it's equal to like t of n minus 2 plus 2 plus 2. So the more you the deeper you get in your recursive calls is what you're going to multiply by essentially, right? So let's say like this is our t of n minus 2. We're going to do our t of n minus 2, and then we're going to find out what t of n minus 3 is, right? Right. And again, we're just following the uh the equation up there. Plus 2 times 2. And then this is going to be equal to t of n minus 3 of plus 2 times 2. If you're starting to see the pattern, is this clicking for you guys a little bit or not at all? Could I rewind a little bit? Yeah. So we have our in the problem, we're given our recursive call function, this t of n minus 1 plus 2. That's what our t of n is. And then we know our base case is t of 1 is equal to 1. So what you need to do is that you need to find some pattern as you continue to do the recursive calls, right? So you would start at like t of n minus 1 plus 2, and then you would go one deeper, right? So you do like t of n minus 2 plus 2, and then you know that you're going to add 2 to that call. Does that make sense? Based off of the equation that we're given for the function call. And then you start noticing a pattern. Like it's going to be t of n minus some number plus 2 times that same number. How do we add 2 again? Because that's the function. That's the function call. We don't know what the returned value is, so we're constantly going to just be adding 2. The deeper you get into the function calls is the amount of times you're going to continuously add 2. That makes sense to you, Nicole? Because we don't know what value the functions are returning. This is just the mathematical formula for the recursive call. So like you'll start noticing a pattern, right? So we'd have t of n is equal to t of n minus 1 plus 2 times 1. This is the first call. T of n is equal to t of n minus 2 plus 2 times 2. You got the second call. You have T of n is equal to T of n minus 3 plus 2 times 3. That's your third call. And then so on and so forth. Right? You guys, you see how that works? That's the pattern that you need to be able to recognize. Yeah. So it's with recurrence relations, it's like figuring out what that pattern is inside of the recursive function. You're not finding the call. You're usually given the call. So like we're given the call in the problem. So we know T of n is equal to T of n minus 1 plus 2. We know that's what the call is. But you need to just like when we're returning recursively and it's usually like plus 2 or minus something, you're constantly going to continuously add that amount for every recursive call. So you end up like multiplying them together. That's just what the pattern is in here. So then you'll end up with like a generalized form of T of n is equal to T of n minus k plus 2 times k. That's where like the k value comes in from. Right? So then for the base case, you want T of 1. So we know that the recursive functions completely end. So at some point, n minus k has to equal 1. So you need to solve for k so that so we know like n minus k is equal to 1. This is our base case. We need to find out what value of k gets us that. So that's just normal algebra. K is equal to 1, and then it's just 1 minus n, I believe. I'm sorry, it wouldn't be 1 minus n, it'll be k is equal to n minus 1. There we go. Brain fart there. So once we have that, we're going to plug it back into our original function, right? So T of n is equal to T of 1 plus 2 times n minus 1. So T of 1 is just 1, right? We know that much. We got that here. So then we end up with T of n is equal to 2 times n minus 1. And that just means that T of n is equal to 2n minus 1. This is basically like what your final like recurrence relation would look like. Where did n minus k equals 1 come from? So we know what our base case is. We know that when T of 1, when we have our recursive call of T of 1, we know that it's equal to 1. And so we know that there's a pattern in the recursive call of T of n minus k plus 2 times k. So we need to figure out at what value k needs to be to meet that base case. So that's why we do n minus k is equal to 1, because we know that once that is 1, we've reached our base case, and then you solve for k. another example with division. Let me see if she has one with division. You talking about like problem 2? Let's see. She has t of n is equal to 2t of n divided by 2 plus n, and then our base case is just when t of 1 is equal to 1. Yeah, I got you. I got you. So it's gonna be the same thought process, right? So we're gonna start with our first recursive call, right? So it's gonna be 2t of n divided by 2 plus n. We're gonna go into our first call, right? So we obviously see that it's multiplied by 2, so it's gonna be 2 times our function call, right? So 2t of n divided by 4, right? Because it's n over 2. So you're halving it each time. So half of a half is a quarter, right? Plus n over 2, right? Because it's plus n. So you have plus n. This is where the plus n comes in from. Plus n equals, we're going to end up with 4t because we have our multiplication of n over 4 plus n plus n, which ends up just being 2n, right? So when you basically combine like terms, you end up with 4t of n over 4 plus 2n, right? And then we're going to continue doing our recursive calls until we find some pattern, right? So we'll keep going. We'll say t of n is equal to 4t of n over 4 plus 2n. We're going to do another recursive call. So we know it's going to be 4 times 2t. Again, it's 3n because n gets multiplied by 2. It gets passed, but another n is added afterwards at each call. Okay. Excuse me. Right. So eventually, like you'll keep on just adding, like for this call, it wouldn't be it would be 3n. Right. So you already noticed the pattern. So we have n over 8 plus n over 4. Sorry, it should be like this. There we go. For them. Or them. Plus n over 4 plus 2n, because remember, we still have our 2n here. And then we're going to set that equal to 8t n over 8 plus n plus 2n. And like he already said, t of n is going to equal to 8t of n over 8 plus 3n.
Oh, really?
And you'll just keep on going and going and going and going. And so like you'll figure out that,
No.
excuse me, this 4t is our second iteration. The 2t of n over 2 plus 1, that's our first iteration, right? So this is first iteration. This 8t is our third iteration. And you have to notice some pattern, right? So for instance, the pattern would be 2 to the power of k So K is going to be whatever your pattern is, right? 2 to the power of K, and then you're going to have your function call of n over 2 to the power of K plus K times n,
Okay, yeah. Right,
right? And then so
but you don't,
the same thing as before, we want to figure out our
okay,
base case. So we're going to let n equal 2 to the power of K. And we need to solve for K. And so using right, you're just gonna decipher the equation. You're gonna find some pattern, and then once you figure out that pattern, you're gonna solve for when K equals the base case. Right. So for instance, like you would end up with K is equal to log n,
okay,
right? Because you would take the log of both sides and to get the K down. Um, and then you'll plug it back into the equation. So T of n is equal to 2
left for the day. Are
log
you gonna verify
n
Dr. Patel so he can read it and read
T
it right away?
of 2 to the power of K over 2 to the power of K
Um, yes, please. If
plus log n.
yeah, because he
N.
needs to know the information and I'll have,
And
Echo will probably call him
this will
too,
equal
because he has to read it, otherwise it's not a stat. You know what I'm saying? Okay,
n
you're, no problem. He
times
just left, he just came in for two
T of
stats. So
1
it's been one of those days, but no
plus
problem. I will call him
log
and let him
n
know,
n
if you
is
don't
equal
mind
to
calling Dr. Patel, just to
n
inform
plus
him so
n
that Echo
log
Tech can call him. Thank you,
n.
dear. Thank you so much. Bye.
So this is the same thing. We know what our base case is. It's 1. Um, so we end up with n times 1 plus log n times n. Um, this would result into being T of n plus n log n. It's confusing. Sometimes it's yeah. Yeah, it's gonna be GG's for recurrence relations. I know. I know.
Oh, yeah.
It's basically pattern recognition though. So you need to
Baby.
find some pattern inside of the recursive call by doing iterations of the recursion. And then once you realize what that pattern is, you can use that pattern to find out. It is too late, Allison, but it's okay. It's okay. This is what, quiz 3 for us? Or is it quiz 4? I think it's quiz 3. We should be good.
See what he said. I said because someone has to
Um,
tonight, that's why it's not a tattoo, but I understand. She was really nice. I think she's just
2K,
freaking
2K
out.
is just 1. Yeah.
The baby was just born. Yeah, decompensating with a.
Yeah. Okay. I'm just looking it over again. Because this would end up
Yeah.
just being 1. That's where we get our T of 1 from.
And you would call him to see whether or not he's gonna be reading it or does he need to. come
Trying to
over?
see how we just jump to
And
N.
then just left. I said, they're gone.
But I think that's as much help as I'm gonna be on recurrence relations, unfortunately. I can add like resources. I can send it in the Discord and the group me for everybody to like watch.
Oh shit, I found out. Dr. Simon.
Sorry, sorry, it was just getting
Dr.
loud in the
Simon put in-
background.
He put in another one.
He didn't even call, did he? Tragic. For the first iteration, how did you instinctively know to times 2 by the OG questions and also add n over 4 in there along with plus 2 n over 4? Blah blah blah. You're talking about here, that n over 4. Right. So remember, it's going to be plus n in our recursive call, right? So our n from the previous our previous recursive call is n over 4. So when we do another recursive call, that is the previous n. That's why you're adding n over 4. And then like for instance here, n over 8 is the n for that recursive call. So when you do another call, you'll be adding, I think it's n over 16 plus n over 8. That makes sense? And then you see we're multiplying the function by 2. So it goes from 2, 4, 8, 16, 32, so on and so forth. That's the pattern that you need to recognize. All right. Unfortunately, guys, that's all the time I have for tonight. I will post some recurrence relations resources in both of the Discord and the group me. If you guys, yeah, of course, of course. If you guys need resources on trees and stuff, I can send that over too. I don't want you guys to be like blindsided by worrying heavily on the recurrence relations and then see a tree problem and be like, oh shoot. So I'll send some of that over tonight as well. All right. But if nobody else has anything else, you guys have a good night and I'll see you all in the morning. Good luck, every guy.